Hello everyone, welcome to my class. Today we are covering improper integrals. Let me start the class right away. These improper integrals are a definite integral. So first, quick recall. In calculus 1 we define the definite integrals and denoted by f(x) dx from a to b with two assumptions. First, the domain of integration is finite. Second, the integrand function is continuous on closed interval AB. So now in these sections, we consider a definite integral where one or both of the above conditions do not hold. So that is, either the interval of integration is not finite or the integrand function is not continuous. Then such integral is called improper integral. So let me give you the definition first. Improper integral or definite integrals, integral f(x) dx from a to b is called an improper integral where either the interval of integration is unbounded, that is either a is infinite or b is infinite, or both a and b are infinites, or the integrand function is not continuous, that means function has a vertical asymptote on the interval AB. There are three types of improper integral: type 1, type 2, type 3. In the type 1, domain is infinite or unbounded, say negative infinity to all the way to b, or a to plus infinite, or both side negative infinity to positive infinity, means both endpoints are infinite. Type 2 improper integral where integrand function is not continuous, that is f(x) has a vertical asymptote on the interval AB. And type 3, both the domain and the integrand functions are unbounded, and the type 3 can be computed using either case above. So quick example. For example, example 1, example 2, example 3, example 4, and example 5. So example 1 has a graph. So the first example is integral e to the power negative x from -2 to infinite. So here's our interval of integration is infinite. So this is a type 1 improper integral. Example 2, integral of 1 over x from 0 to 2. So here our interval is finite, but integrand function has a vertical asymptote at 0. So this is a type 2 improper integral. Similarly, in the third example, integrand function has vertical asymptote at 2, and at the same time our interval of integration also infinite. So this is a type 3 improper integral. I hope it makes sense to you all so far. And then the last one, I gave you the picture here for 0 to 1 natural log of x. So here integrand function has vertical asymptote at x equals to 0. Great. So the question at this time arises how to evaluate such integrals. So the idea, integrate it over a slightly smaller region and then take a limit. So it involves two parts. Compute the definite integrals on a smaller region and then take its limit for type 1. Let me scroll down. So a to integral of f(x) from a to infinite, then forget the infinite for a moment and truncate a certain finite number. So some finite number is b, let's say b. Then compute the definite integrals a to b f(x) dx and then take the limit b goes to infinite. Let me pause for a second. I hope this makes sense to you all. Similarly, improper integrals f(x) dx from negative infinity to b truncates at some number less than b, that's a, and compute the definite integrals a to b f(x) dx and take the limit the lower limit a goes to negative infinite. Awesome. Similarly, improper integral of fx from negative infinity to positive infinity. So that means I need to truncate it at certain point here, c, and then the same idea for the negative infinite. So take limit a goes to negative infinite and a to c fx dx plus truncate at certain point or certain number b, finite number b, then evaluate c to b fx dx, the definite integrals, and then take the limit as b goes to plus infinite. I hope it makes sense to you all. One quick note, make sure each integral on the right side is improper at only one place, either at the lower limit or at the upper limit. We cannot have improper in both places. So for example, here is our improper is on the lower limit, here is improper is on the upper limit. Great. One quick warning, improper integral can only be evaluated as limit. And improper integral fx dx from negative infinity to positive infinity is not equals to the definite integral negative t to t fx and limit t goes to infinity. So we cannot write this way. Awesome. Let's move on. Definition of convergent and divergent. The improper integral is called convergent, and in short form we write CGT, convergent, or divergent, we used to write it DGT. This is my way of writing CGT and DGT for convergence and divergence. If the corresponding limit exists as a finite number, in latter case the limit means it doesn't exist. In the latter case the limit either dne does not exist or equals to plus infinite or minus infinite. So this means the improper integral convergent if the limit exists, and we know in calculus 1 not every function has a limit, right? Sometimes limit may not exist. If limit exists, then the improper integral is called convergent. It's a new terminology. It's same as the limit, corresponding limit exists. And we know about the limit convergence, limit exists or doesn't exist from Calc 1. If the corresponding limit does not exist, then we call the improper integral divergent. So now two fancy names here, convergent and divergent. Okay. So for convergence integrals, improper integrals fx dx from negative infinity to a and improper integral fx dx from positive a to infinite, we can add these two convergent integrals and we define the improper integrals fx dx going from negative infinity to positive infinity. Means we truncate at a, and if you want to go from this side to the left side to the right, then we truncate at a, and we first integral ends at a, second start from a to infinity. Awesome. I hope so far so good. Now the last line here, the left side integrals, convergent if and only if. This is if and only if, IFF. If and only if means both directions too. Left side implies right side implies the left side. So left improper integrals convergent if and only if both integrals on the right side convergent. If any one of the improper integral on the right diverges, then automatically the left integrals diverges. So to show left hand side, this left integral divergent, all you need to show one of the right side improper integrals diverges. But to show left integrals convergent, we have to show both of the improper integrals on the right converges. I hope this makes sense to you all. Now let me scroll down. Now for type 2, remember our type 2 improper integral is the integrand function is not continuous, means it has a vertical asymptote. So for type 2 improper integrals, suppose that the integrand function is continuous on the interval except at a point C in between AB, where x equals to c is a vertical asymptote. Then there are three cases. Our vertical asymptote may be on the right hand point, or maybe the left hand point, or somewhere in the middle. So let me go to the first case. Suppose function is discontinuous at right hand point, at B here is discontinuous. Then define the improper integral a to b fx dx equals to, take this c smaller than b and define the definite integrals of fx from a to c fx dx, and take limit c goes to b from left side. C goes to b from left side. Hopefully this makes sense to you. Similarly, case 2, suppose function is discontinuous at left hand point, means we have a vertical asymptote on the left hand point at a. Then to define the improper integrals of fx from a to b, take a number c bigger than a and define the definite integrals of fx from c to b, and take the limit c approaches to a from right side. So this is limit c tends to a plus definite integral c to b of fx dx. Similarly, case 3, suppose this times our function is discontinuous at a point c in between AB. That means we have vertical asymptote here. Then to define the improper integrals of fx from a to b, because I need to pick a number smaller than c, bigger than c, and define one definite integrals and take limit. This number goes to c from left, and another definite integrals from this number s, which is bigger than c, so s to b, and then take the limit s goes to c from right side. That's what I did here. So integrals of fx from a to b equals to, so obviously the point c I have to throw out, so a to c fx dx plus c to b fx dx, and then c, my function is not defined at c, so that means I need to find a number smaller than c, and let's say I found a t, and define integrals of fx from a to t and take limit t goes to c from left side. So this is the first term here, the first integral on the right. Similarly, the integrals fx dx from c to b is not defined at c, so I need to pick a number bigger than c and define the integrals of fx from s to b, because s is bigger than c, and then take a limit s to c from right of c. So this is limit s tends to c plus integral of fx from s to b. I hope this makes sense clear. So please pause the video and go over a couple of times, because this definition is important. Great. Now let's move on. Now let's do some example. Worked out example. First example. That's better. Evaluate the improper integrals of 1 over x from 1 to infinite. So here's our, this is of type 1 improper integrals. Our domain of integration is infinite, so I need to truncate a finite number and compute a to that finite number integrals, and then take limit that finite number to infinite. That's the idea. So first, write integral 1 over x from 1 to infinite equals to integral 1 to b of 1 over x, and take b limit goes to infinite. Hope this makes sense to you all. And now it involves the two steps. First, compute these definite integrals. Let's do step by step. And then second, take a limit. So step first, compute the definite integrals. Definite integrals of 1 over x from 1 to b. You know the integral of 1 over x is natural log of x. Evaluate at 1 and b. So natural log of b minus natural log of 1. Natural log of 1 is 0, so I have only l and b. Next, take a limit. Limit of left side as well as limit of right side. So limit b goes to infinite, 1 to b, 1 over x dx. I just copy this one here. Equals to limit b goes to infinite of natural log of b is simply infinite. So this, we found the value of integral 1 over x of from 1 to infinite is infinite. That means this improper integral is divergent. Correct. Great. Let's move on. 2. Evaluate the integrals of 1 over x squared from 1 to infinite. So again, let's begin the solutions. We first evaluate the definite integrals. I'm truncating at finite number b, so evaluate integral 1 to b of 1 over x squared. The integral of 1 over x squared is minus 1 over x. So here what you do, you take x squared to the numerator by making the power minus 2, so x power minus 2, and then use a power rule. X power negative 2 plus 1 is negative 1 over x to the, over negative 1. So it gives you negative 1 over x, negative 1 over x. And then evaluate at 1 and b. So here, when you put the lower limit, it gives a minus, so that's why this minus plus 1 over 1 is 1, and then minus 1 over b. I just switch the position here. In the next step, take a limit b goes to infinite. So limit b goes to infinite of the definite integrals we used in part A equals to when limit b goes to infinite, this fraction goes to 0, so we have only 1 left. That means the value of this improper integral is 1. That means the given improper integral is convergent. Great. Let's do example 3. Evaluate improper integrals of 1 over radical x from 1 to infinite. So again, truncate at finite number, compute the definite integral, then take the limit. That's the idea. So part A, definite integrals of 1 over radical x from 1 to b. So take radical x in the numerator, so this becomes x to the power negative 1/2. Then use the integral formula. So this is the power formula. So in the next step, x to the power negative 1/2 plus 1 means plus half divided by plus half. So that means you just switch that half, so it goes 2 on the numerator. So 2 times x to the power half means radical x. I hope this is not hard for you all. So 2 times radical x, and the limit 1 to b equals to put upper limit b minus lower limit 1, so 2 times radical b minus 2. And the next step, take the limit b goes to infinite of this integral in part A. So that means on the right side, take limit b goes to infinite of radical b is infinite, so then everything is infinite. So the given integral is divergent. So see, it's following the pattern here. So if you have 1 over x, what's the power? If you have a power 1, divergent. If power is 2, power 1 over x, power 2, then convergent. If power is 1/2, means less than 1, divergence. So in fact, this is true. We also call p-test. The improper integrals of 1 over x to the power p is a positive number, This converges if p is greater than 1 and diverges if p is less than or equals to 1. Great. Now do example 4. Determine whether the integral is convergent or divergent and evaluate if it is convergent. The improper integrals of 1 over x minus 2 to the power 3/2 from 3 to infinite. Great. So it's a type 1 improper integrals. There are two steps. First we compute the definite integrals and then take a limit. So let's compute the definite integrals 3 to b of this integrand functions, and next take the limit b equals to infinite. So begin the solutions. Part A, so definite integral 3 to b of x minus 2 to the power negative 3/2. I took this denominator to the numerator by switching the sign in the power. Then by u substitution, this is evaluated as this way. So x minus 2 to the power negative 3/2 plus 1. So okay, let's just focus on the power. Negative 3/2 plus 1 is minus 1/2, and divide by 1/2. Divide by minus 1/2. And we know that dividing is same as multiplying by its reciprocal. That means you flip that 1/2. So that's why this minus 2, oops, this minus 2 comes here. So minus 2 times x minus 2 to the power negative 1/2, and limit is 3, sorry, the lower limit is 3, upper limit is b. Then put, first evaluate the lower limit so that this minus goes away. So put x equals to 3. So 3 minus 1 is 1. 1 to the power negative 1/2 is 1. So I have only 2 left here, 2 left here. Then minus, for the upper limit, put x equals to b. So 2 over radical b minus 2. Here again I switch the positions. First I evaluate on the lower limit, so I have a plus sign here. Okay. And the next step, take a limit. Take limit, now b goes to infinite. That means this on the right hand side, the second term goes to 0. So then I have only 2 left. That means we found the value of this given improper integral, which is 2. So that means the improper integral is convergent. Great. Let's move on. Let's take example 5. Determine whether the integral is convergent or divergent. The integral is 0 to 5 of 1 over x minus 1. This is not type 1 because we have a finite interval. This is the type 2 because this integrand function is not defined at x equals to 1. I have a BA at x equals to 1. So let's rewrite. Integral of 1 over x minus 1 from 0 to 5 equals to, so let's put 1 here, upper limit for the first integral, and 1 on the lower limit on the second integral. So 0 to 1 of 1 over x minus 1 plus integrals 1 over x minus 1 from 1 to 5. And now I need to throw this 1 out, throw 1 out. So I need to put another numbers here first. So let's go from 0 to b, same integrand functions, and then take the limit. This b goes to 1 from left side because I pick a number b less than 1. And then plus as it is. Similarly in the second integral, pick a number bigger than 1, so I pick a. And let's evaluate this definite integrals of 1 over x minus 1 from a to 5, and then take a limit. This number approaches to 1 from right side. I hope this setup makes sense to you all. Let's move on. And now let's evaluate here. So the next step here, limit b tends to 1 from left. The integral of 1 over x minus 1 is simply natural log of x minus 1. Value goes from 0 to b. Similarly, plus limit a tends to 1 plus natural log of x minus 1 from a to 5. Then put a big x equals to upper limit, x equals to lower limit 0 in the first integral, first limit. So limit limit b tends to 1 minus ln, so b minus 1. For the lower limit, when you put x equals to 0, then you have ln 1. ln 1 is 0, so I don't need to write down the lower limit value here. Similarly, the second term, just on the upper limit here, limit a tends to 1 plus limit 5 minus 1 is 4. So that's a finite number. Great. But when you take a big approaches to 1, then this becomes ln 0. ln 0 is infinite. So we just stop here. We don't need to evaluate the second one, but we already computed. But if any one of these improper integrals diverges, then automatically the left side integral diverges. Great. Hence the given integrals diverges. Awesome. Now let's move on. Example 6. Evaluate the integrals of 1 over x squared from -1 to 1 dx. It's a type 2 improper integrals. The integrand function is not defined at 0. So let's rewrite the given integral in two integrals. So one is definite integral, one is improper integrals of 1 over x squared from -1 to 0. And another one is from 0 to infinite of 1 over x squared dx. Similarly, this picture is here. So the first integrals, limit t tends to 0 minus 1 to t of 1 over x squared plus limit s tends to 0 from right, integral of 1 over x squared from s to 1. I hope this setup makes sense to you all here. Then let's evaluate this limit one at a time. And we know if one of the improper integral on the right diverges, we don't need to evaluate the another integrals, then automatically the left side improper integrals diverges. But to show the left side convergent, I need to show both of the integral on the right converges. That's the idea, okay? So then let's evaluate the first integral on the right. So limit t tends to 0 minus -1 to t of 1 over x squared. So copy the limit as it is. Limit t tends to 0 minus integral of 1 over x squared is minus 1 over x, and then the limit 1 to t. Again, copy this limit t tends to 0 minus, means 0 from the left. So put t equals to x equals 2 and x equals to 1. So again, I put the lower limit to take out this minus sign. So 1 over 1 is 1 minus 1 over t. And take the limit when t goes to 0. So then this goes to infinite. So that means this limit goes to negative infinite. This minus gives you negative infinite. So that means stop. We don't need to evaluate the second limit or second improper integrals. One diverges means the left side integral diverges. Hence, the given integral diverges. I hope this makes sense to you here. So quick examples, and they are very, very useful. So here is a improper integrals. Improper integrals e to the x from negative infinity to 0. It turns out to be the area is 1. Another improper integrals of ln x from 0 to 1. Again, it turns out to be negative 1. The area turns out to be negative 1 because it lies below the x-axis. But if we take absolute value, then these two integral gives us the same numbers 1. Interesting. And then the Third example here. Improper integrals of e to the power negative x from 1 to infinite is 1 over e. Great. So all of these three integrals are convergent integrals. So please work out and show the value of these three integrals are given in the picture here. So this is e to the 1 over e, this is -1, this is +1. Great. Let's move on. Convergent divergent test for improper integrals. There are three tests. The P test we discussed above, comparison test, and a series test. In the series test, we study more on chapter 11, infinite sequence and series. So now let's talk about comparison test. Suppose you have two continuous functions with fx is greater than or equals to gx. So here is your function f lies above g here for all x in a to infinite. Then the condition is if a to infinite means improper integrals of fx converges, then improper integrals gx converges. So that means on this inequality, if the functions, if the bigger functions converge, then smaller functions converges. The two, if the lower functions diverges, then the bigger functions diverges. And that's true if you focus on this area here bounded by g function and bounded by f functions. If this smaller area diverges, means if this smaller area is infinite, then obviously the bigger area also infinite, because the bigger area is now bigger than infinite, right? And in the first case, if the area bounded by this bigger function is convergent, means finite number, then obviously this smaller area bounded by g function is automatically smaller than that numbers we got from integral of f. It means automatically convergent. I hope this makes sense to you all here. Note, if you are smaller than something that converges, then you converge. Yeah, that's true. Sometimes these inequalities are useful. That means the natural log function is dominated by radical x is dominated by x. That means these are the algebraic functions, and these functions are dominated by the exponential functions, and then this function is dominated by the x to the x, some weight type functions. Awesome. Now C, series test, or we call integral test in chapter 11. Suppose our function is continuous, positive, and decreasing on interval 1 infinite, and an equals to function of n. Then the improper integrals converges if and only if the corresponding series converges. So I have not talked about series, but you have seen this series notations in Riemann sum in calculus 1. So that's the sigma notations, and that's a an with n is index. So that means a1, if you put n equals to 1, a1, then sigma means plus, put n equals to a1 plus a2 plus a3, blah blah blah. So that series converges if the improper integral converges. Okay. One final remark. Several results about improper integrals are worth remembering as we revisit some later in chapter 11. Yeah? Great. Now let's do another example. Determine whether each of the following integrals are convergent or divergent using a comparison test. Great. So first example of example 7, first part, integrals of sine square x over x squared from 1 to infinite. So it's a hint. So we know -1 is less or equal to sine x less equals to 1. We know sine x maximum value is 1 and minimum value is -1, right? So we can bound sine x by 1 to minus 1 and plus 1. This is same as saying sin square x is less than or equals to 1 and sin square x is positive, right? Absolute value of sin x is bounded by 1. And now in this inequality, let's divide by x square. By the no matter what x is, either positive or negative, x square is positive, right? So I'm dividing by both sides by positive number, so this inequality remains as it is. So then 0 over x square less or equals to sin square x over x square less or equals to 1 over x square. I think this type of inequality we worked in Calc 1, the squeeze theorem, right? Yeah. So now, since on the right hand side this 1 over x square being a p-test or the p-test, the p is 2 is greater than 1, so this series converges. Then by the comparison test, the integrals of sin square x over x square from 1 to infinite converges. So let me take you to the p-test here. Here, the improper integrals of 1 over x to the p from 1 to infinite converges if this p is bigger than 1 and diverges if p is less than or equals to 1. So now in our example, let me scroll down again. In our example here, so integrals 1 to infinite 1 over x square, here p is 2 greater than 1, so this converges. So the bigger integral converges means the smaller integral automatically converges. So this converges. But here we don't know it converges to what number, but at least we can guarantee that the given integral converges. I hope it makes sense to you all here. Next, another example 2. Evaluate the improper integral of e to the power negative x square from 1 to infinite. So let me establish an inequality and then apply the comparison test. So for x greater than or equals to 1, x square is greater than or equals to x. So this is true. Right? Because I'm picking x is greater than or equals to 1 because my integral starts from 1 and then infinite. Okay? It's from 1 to infinite. So for x greater than or equals to 1, x square is greater than or equals to x, that's 2. Then multiply by negative, then negative x square is smaller than negative x, that's 2. And raise both of these values to the same base e. Then the same inequality 2, right? E to the power negative x square is less than or equals to e to the power negative x. This is true. And now, the improper integrals of e to the power negative x from 1 to infinite is a convergent one. Do you remember this? I gave you as a class work here. This integral. This area is 1 over e, which is a finite number. So then this converges. So this integral is just 1 over e. Even I worked here and geometrically I showed you earlier. This converges, means the bigger integral converges, means this integrals by the convergent test, integrals of e to the power negative x square from 1 to infinite converges. But again, we don't know it converges to what number. But here all we are determining whether the given integrals are convergent or divergent. Okay, great. Similarly, part 3. Let's establish another inequality here. So what is true here? So here for x is greater than or equals to 0, my improper integral starts from 0, then tan inverse x is less than pi half, right? Because the tan function has asymptote at x equals to pi over 2, then the inverse is smaller than pi half. And we know pi half is less than 2, right? So that means tan inverse x is less than 2. This is true then. Let's forget this middle part. Let me hide here. So tan inverse x is less than 2. Then look at the questions. I have on my denominator 2 plus ex. So let's divide both sides by 2 plus ex since this number is positive. 2 is positive. Exponential function is always positive. So this is a positive number. So the same inequality hold. So then tan inverse x over 2 plus e to the power x is strictly less than this 2 over 2 plus ex. And we know from this last inequality, obviously true, because I just dropped the 2 out from my denominator, means I make my denominator bigger. No, I make my denominator smaller. So smaller denominator means bigger the fractions, right? Great. So then first inequality to the last inequality, this is true. Then this left side is the given integral here, right? So let's take the integrals from 0 to infinite. Then the right side integrals is the convergent integrals. That's the integrals that we discussed in second part here. So the right side is convergent. Sorry, the bigger integral is convergent. And here is the right side. That means the smaller integrals means integrals of tan inverse x over 2 plus ex from 0 to infinite obviously converges. Great. Awesome. So we finished this improper integrals as well as we finished the chapter 7. So thank you.